Hello and welcome back to my physics channel. Today we'll be talking about some key equations that we use for kinematics in specific. So the first equation that we're going to be using in this unit a lot is actually going to be the equation delta D is vector is equal to 1/2 a acceleration delta t squared plus v1 delta t. So that's the first equation, delta d. Next equation is going to be delta t is equal to v2 vector delta t minus 1/2 acceleration times delta t squared. The next equation is going to be v2 squared is equal to v1 squared plus 2a delta d. Make sure to not drop your vectors on any of these because if you build a good habit right now, these good habits will carry over. And our last equation is going to be delta d is equal to 1/2 v1 plus v2 times delta t. So these are the kinematic equations that we have right here that we're going to be using for a lot of the kinematics that we do moving forward. And with a lot of the questions, what we're going to have to do is we're actually going to have to rearrange a lot of these equations, and sometimes we'll even have to use quadratic formula. And if you may be wondering like, oh, like where are you going to have to use a quadratic formula? If we look at this equation right here in specific, if we look here, we have delta d is equal to 1/2 a delta t squared plus v1 delta t. We have this, right? Sometimes you'll be lucky and your delta d will drop out, or maybe this v1t will drop out and you're left with 0. And you'll be lucky and you won't have to use a quadratic formula. But sometimes you won't be as fortunate and none of your terms here will drop out. If none of your terms drop out, oftentimes when you're looking for time, actually, you might have to use the quadratic formula. How and why we would need to use a quadratic formula? Well, the reason is, let's say we're looking for time, right? Because if you look here, we actually have a quadratic. If we move this d over to the side, we'd have 0 is equal to 1/2 a delta t squared plus v1 delta t minus delta d. Well, this delta t actually, if it maybe if it helps to see, maybe if it helps you see better, that can be looked at as maybe an x. So 0 is equal to 1/2 a times x squared plus v1 times plus v1 times x minus delta d. We had a quadratic, a linear, and a constant term right there. And whenever we have all of these together, we know that we have to use a quadratic formula. How would we use a quadratic formula here? Well, we'd use these two terms as our a value, this term as our b value, and this term right here as our c value. And we can just input the numbers. We can go a is equal to, b is equal to, c is equal to, and we'd go from there. But we'd only have to use the quadratic formula in this equation if none of the terms drop out. If none of the terms drop out, that means that we may have to resort to the quadratic equation where we're looking for time, because a quadratic equation will give us 2 times. Maybe the question states that you throw a ball here. It may give you the time of the ball right here and here. It just depends what the time is. Maybe if the time's negative, you know you can drop that time out. It just depends what you're looking for. It's really up to the question. But you will get a T1 and a T2. Just like how in a quadratic, you'd have x1 and x2 because you get 2 roots, right? So it's really important to make sure that if none of your terms drop out, you do use the quadratic formula. And sometimes you have to maybe just double check. Maybe something does drop out. Maybe you start from rest and it drops out. Or maybe your distance ends up being 0, depending on the question. Or maybe the acceleration drops out. Maybe this one drops out. You just have to read the question carefully. But in case that does not happen, you will have to use the quadratic formula, possibly for some of your questions. Not all, but possibly for some. In the next part of this video, I'll take up some questions using our new formulas here, and we can try to discover what we may need and what we're looking for. Because some of these equations, the reason they're helpful is because we're actually like, some don't include some certain things and some others do. Like for this equation, you don't need V2, right? There's no V2 in this equation. So if ever you're trying to, you have a bunch of given, but you don't have V2, you know that this equation will most likely help you out and can help you try to work through that question. In this one right here, you don't have V1. So if you don't have V1 in your question, or if it's not stated, you know you can probably use this equation right here if you're looking for any of these variables. This one, you don't have time. So if you don't have time, you know you can try to figure out time without the need for it in your given, right? This one right here, you don't have acceleration. So if you don't have acceleration, it just really depends for you to look at what you're given and try to match up what the best formula might be. And sometimes you can get a formula that will have all of these, like maybe this formula can work and this formula can work. So then you have to look at what formula will fit it best, which will have the most variables, and which one you can do the most algebraic manipulation to. You don't really want to sub in numbers in, like you don't want to, maybe let's say you can be like, oh, I can get V2 by doing some rearrangements or some algebraic manipulation, and then you sub in the number into here. You want to try to avoid that. You want to try to just use what you're given and try to evaluate from there. But next part of this video, we'll take up some questions and we'll look how these equations can come into play. Okay, in front of me I have some practice problems that we're going to use some of these equations up here to solve with. So the first question, it says, remember we always want to start with the given. So a sports car approaches a highway on a ramp at a velocity of 20 meters per second east. So a given, so our V1 is going to be, remember to set east as equal to positive. Remember to always define direction to, not to save time, but to make sure everything's cohesive. So east is positive. And then we'll go 20.0 meters per second as our next part. And it says if the car accelerates at, so we'll go acceleration is equal to 3.2 meters per second squared. So we know that the acceleration is going to be that. And it says the delta t is going to be 5 seconds, right? So it asks, what is the car's displacement? So our required to find here is delta d. So you'll notice that we can't use the equation of motion that we had before. We can't use the one where we had the velocity or distance. We can't use any of those. Like we don't have anything that will give us delta d using any of this from before. But now we have a new equation, which is this one right here. Delta d is equal to 1/2 a delta t squared plus v1 delta t, right? Let's see if that'll work. So we can go delta d is equal to 1/2 a delta t squared plus v1 delta t. In this question, we have v1, so that's good. We have delta t, which is also good. And we have the acceleration, which is all the things we need for delta d. So this one, it goes off pretty easy. We can just go delta d is equal to 1/2 3.2 meters per second squared times 5 seconds squared plus 20.0 meters per second times 5 seconds. Oops. 5 seconds, right? So we can just do all of this. And if you punch this into a calculator, you approximately should get something Let me just punch this in my calculator. You should get 140 meters. And that is your answer. So that's how we can solve this one. Let's look at the next one. It's a little more tricky, but there's a few things we can look at. So given, a car is traveling at an initial velocity of 15 meters per second east. So let's just go ahead right away and set east as positive. 15 meters per second east. When the driver applies the brakes, the car comes to a stop after traveling 30 meters east. What is the car's acceleration? So we know that the V1 is just going to be 15 meters per second. So, and then we know the delta D is going to be 30 meters vector, because it says the car the car comes to stop after traveling 30 meters. So if we had a car right here like this, and it was moving here, but then the driver wanted to apply the brakes, he still ended, like, he's put his foot on the pedal right here to stop, but he still ended up traveling 30 meters before he came to a full stop. So he still had a delta displacement of 30 meters in total, give or take, right? So when we look at here, we know that delta D is going to be 30 meters. That's all the numerical numbers we're given. But again, we have to read closely into the question, and we'll notice that it says the car comes to a stop, right? Which means it's the same as it coming to rest. And what does come to rest mean? Well, it means if it comes to rest, it means that the velocity is 0. It's like if you're sitting down right now at rest, you're not moving, so your velocity is 0. So now, when it says we're looking for the car's acceleration, so we can go required to find, and basically, now we're looking for A, so acceleration. So you may be like, oh, why can't we just use A is equal to V2 minus V1 over delta T? Well, you quickly realize that we have two unknowns. We have this as unknown, and we have this as unknown. So we have two unknowns. We can't use that. Well, let's look at what equation we have that may be able to help us. So let's look at what we have. We have a V2, okay. We have a delta D and a V1. So this has V2, V1, and delta D, but it has a delta T, and we don't have time. This one up here, it doesn't have V2, so we probably shouldn't use that. We should use whatever's in our given. This one here has a V2, but it doesn't have a V1, and it has delta T. This right here has V2, V1, and delta D, and acceleration, what we're looking for, and no time. So we should probably use that equation. So that's going to look like V2 squared is equal to V1 squared plus 2A delta D. So that's our equation that we have. So let's look at what we can do with it. So we're looking for this. So we really want to get acceleration by itself. So what are some things that we can do here? Well, we want to algebraically manipulate it, right? So we want to try to move things over and try to get acceleration by itself. So the first thing we should probably do here is move this V1 over to the side. How are we going to do that? Well, the way we're going to move the V1 over is because it's added here, it's plus V1, right? We're just going to move it over by doing minus V1. So minus V1 squared. So now we have V2 squared minus V1 squared is equal to 2A delta D. The next thing we want to do here is we want to get rid of this delta D and this 2. Well, how are this delta D and 2 connected to this A? Well, they're both being multiplied by A, right? And the opposite of multiplication is division. So we're just going to do 2 divided by 2 delta D vector. And that'll leave us with V2 squared minus V1 squared over 2 delta D is equal to acceleration. Now, from here, we have everything we needed, so we can just go straight into our solution. We know that our V2 is 0, so actually we can just drop this whole term out. We know that the initial velocity is going to be, we can put a negative sign there, and then we can put 15 meters per second squared over over 30 meters. Well, it's going to be 2 times 30 meters, so we can go 2 times 30 meters, and that'll give us our acceleration. So after you punch this into your calculator, you should get something around negative 3.75 meters per second squared. Now you might be wondering, how are we getting a negative number? Like, how is it negative? Acceleration can't be negative. Well, in this case, it actually is, because we're actually braking. So we're not really accelerating, we're almost decelerating. But also, just because we set east as as positives. So let's say the driver was moving eastbound right here. But when he's applying the brakes, he's actually applying them that way, right? So the car can stop. So because of that, we actually have a negative acceleration here as negative 3.75 meters per second squared. So that's all for this video. Make sure to apply these concepts in your fun work, because if you really want to get good at these concepts, it's really about practicing and trying to rearrange these equations over and over again until you're able to get the right answer. And it's just about practicing, and that's the only way you're going to get better. In the next video, we're going to talk about acceleration near Earth's surface and how we use gravity in our equations.